Okay, I'm here today to talk about wave interference. So when two waves pass through each other or pass through the same space, they cause what's called interference. And an example of this would be like musical beats. If you hear two musicians trying to tune to each other, they are very careful to listen to what would be like these beats. Wah, 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 wah. And the closer to in tune they get, the slower the beats become. So if you're very out of tune, it might be like wah, 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 wah. And the closer you get, it goes wah, 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 wah. And if they're playing at the same time and they don't get interference, that's how you know that they are in tune. Now there's other kinds of interference you get, like the double slit experiment, for example, with light, where you send light waves through and you have two slits they're going through, you end up getting the Doppler effect with two wavefronts, and these wavefronts as they pass each other cause interference. So the double slit experiment takes advantage of both the Doppler, diffraction and wave interference to cause what would be like bands of bright and dark. Take an example here. What we see is that when two waves pass through each other or pass through the same space, you have to add their amplitudes together. And sometimes the amplitude is going to be high and sometimes it's going to be low. Just keep in mind that it's always added from the middle. And I have here a black wave that's moving to the right and a red wave that's moving to the left. I kept them separate colors just to make it easier for you to differentiate. And the waves pass through each other without slowing down, meaning if the wave is going to the right, it's going to keep going to the right at the same speed. The wave going to the left is going to keep going to the left at the same speed. So the amount of interference you get depends on how long the wave goes on for. So if these are periodic waves that are continuing, you could get continual interference. But if it's just a quick pulse, you're going to get a very brief instant of interference. But let's look about what happens when they pass through each other. So the red wave is still moving to the right, the black wave is still moving to the right, and the red wave is moving to the left. But now the red wave has moved a little bit further to the left, and we start seeing interference with each other. And what we find is that when the waves are oriented in the same place such that the crests and the troughs are together, because you have two crests right here, your resultant wave has a very big amplitude. And the trough, because you have two troughs together, you get a very big amplitude here. So for something like this, you end up getting much bigger amplitude because you have crests lining up with troughs. Now, you can also have it where the red wave is not lined up evenly with the black wave. So if instead the red wave still moving to the left looks like this, I'm going to drop this down just a little bit. What you end up getting is one with a positive amplitude here and one with a negative amplitude here. So you get an up and a down. And when you add those together, you end up getting almost complete non-wave for just a split second, because the crests and the troughs will cancel each other out. And we can even make like noise-canceling headphones. Your resultant wave doesn't look like a wave at all. It's just completely flat. It has zero amplitude. And this is the case if they have equal amplitude. If the black wave had a bigger amplitude than the red wave, it would still have much smaller waves. Imagine instead the black wave looked a little bit bigger. Your result would look something like this. You'd get just very kind of small amplitude waves as they canceled each other out. So two types of interference. What we find is that this kind of interference is called destructive interference. So destructive interference is when crests meet troughs. Constructive interference is when troughs meet troughs. So constructive interference is either a crest plus a crest or a trough plus a trough, and you get a big wave as a result. This is different than destructive interference. And destructive interference is when you get a crest meeting a trough, and you get very small wave as a result of that. Again, both waves continue passing through each other. Another term that you might see sometimes is phase. And, phase with an H, P-H-A-S-E. And that is really asking how are the waves lined up with each other. So in phase would be like, that's your one wave, that's your other wave. So in phase is when they are together and you end up getting constructive interference. This is different than out of phase, where you might get something like that and something like this, and that's where you would often get destructive interference. Sometimes you'll also talk about the phase as related to a single wave, like is point A in phase with point B. So if you look at this right here, I'm going to keep talking about phase. A and A are in phase. B and B are in phase, but A and B are completely out of phase. B and B in phase. A and B are out of phase. And I'm going to actually give a specific angle to this. So if we consider that full wave as like 360 degrees, then half of a wave is going to be 180 degrees. So they would be out of phase by 180 degrees. You might have a point C right here, C and C, where C and C are in phase with each other. C is out of phase with A by 90 degrees and out of phase with B by 90 degrees. So 90 degrees, 90 degrees. And again, it gets to the idea that a full circle or a full cycle would be 360 degrees. I think that ends this video on interference right now. Thank you very much for watching.